Recap what we had done last time before we get into today's work. Basically, last time we finished up all the technology and really writing the code we need to solve density functional theory problems and to, in principle, be able to produce the same results I showed you on the first day of lecture. In particular, the structure we're working in is that there's going to be a numerical method to minimize functions. That's what density functional theory boils down to in the end. And I showed you that we're familiar with the simple steepest descent algorithm, which is what we'll be using in our first version of the code. In order to carry out minimization with that kind of a function, no, it's not. Clearly, you need to be able to calculate the gradient to proceed downhill. And on the way down, you're probably going to want to print out the energy, so you need the energy functions. So 2 lectures ago, I showed you how in this algebraic language, we could express the density functional theory energy in terms of a set of unconstrained degrees of freedom, which were some matrix we call W, which contains all the expansion coefficients for some set of non-constrained wave functions. They don't even have to be orthonormal. And then in the last lecture, we kind of showed, or kind of felt some of the power of this algebraic language that we were able to take, pretty complicated derivatives fairly quickly. I mean, you've got to get the hang of it the first time through. It's not completely intuitive, but you can see the power of the approach, and it's manipulatable formally, somewhat like Dirac notation is. In any event, we were able to compute the gradient in this language so that we can then just type the gradient into the computer, and that'll basically, produce the code to carry out the minimization. So we're in pretty good shape for density functional theory. Now today, we're going to take a little bit of a step back because we're going to look at now our Poisson solver and how it behaves. So we're going to have to remember back what we were doing with Poisson's equation. And what I want to focus on today, now that hopefully some number of you have actually gone through and done the assignment, is today is going to be more of like a numerical course day. We're going to look at the numerical performance of these spectral methods that I showed you how we can use to solve differential equations. And I'm going to try to give you some good practices in general, again, for computational and numerical attacks on physics problems. So that's basically the goal for the first part of today. Then depending upon how we're doing on time, likely what we'll do after that is maybe take a little 5-minute break and then run upstairs, and then I'll do like a little mini lecture continuing the main thrust of the course, which is that, okay, you have the simplest minimization algorithm, and you actually will, on the next assignment, which is due next Tuesday, do a calculation of a DFT model of a quantum dot. Okay? But in order to be able to do something really real, like a hydrogen molecule, which will be the third assignment, it's just going to take a long time with this very simple algorithm. So we're going to have to improve upon our minimization methods. So the second half of today's lecture is going to be looking at advanced minimization algorithms. So again, you'll learn some good numerical methods here along the way. And I'll show you how to analyze the performance of numerical methods in order to try to improve them. So I think it'll be kind of fun. So now, let's see here if I did this right. I should be able to get my screen back up so we can see the other half. So we had built this code following our algebraic framework to solve Poisson's equation. And some of the details in our let's see, this is going to work for me. Does that look fuzzy, or is it just me? So the details of the actual calculation we're carrying out, remind ourselves, is that what we have is some cubic box, and in the assignment we made this box 6 bore on the side, and we laid out some uniform grid inside that box where we had, I think, 20 grid points along the first dimension, 25 along the second, and 30 grid points along the third. And then within periodic boundary conditions, we put a couple of Gaussians inside that box. And I had a little, it turns out I had a narrow positive, the charge distribution is the difference between these 2 normalized Gaussians. I had a little narrow positive Gaussian in the middle of the cell, and then centered in the same location, I had a bigger, fluffier one with a minus sign. And here I had written down the respective widths of them. So the minus one is the one here with the wider width. And then basically the game is we're going to calculate the electrostatic energy of that charge distribution. That's the bottom line of what we had calculated. Now, analytically, that might be something like U being the electrostatic energy is our favorite integral, dq gar prime, nr prime over r minus r prime. Now, there are a few subtleties here. One is that, although we're thinking of this as just two Gaussian balls of charge centered on each other, sitting in the middle of the cell, actually we have to recall that because we are using a spectral method, we are working in periodic boundary conditions. Right? So over here, I can't draw them all, but it's kind of, but off to the right of this, there's another image. I'll draw it like with dashed lines, and similarly off to the left. And in there, there's another copy of these two Gaussian balls, like so. So we're not really calculating the electrostatic interaction of these two Gaussian balls, but rather of a periodic array of such balls. And I think we want more space here on the board till we get to the analytic part. Now, fortunately, though, I've chosen things so that periodicity shouldn't matter very much to us, right? We've got two Gaussian balls of charge, and as you know from Gauss's theorem, since these are spherically symmetric charge distributions, and they're carrying a net zero charge, outside of them, by Gauss's law, outside for Gaussian, you never quite reach, but it decays to zero very quickly, you'll have zero electric field pretty quickly outside these Gaussians. And that means then that whatever's going on in one of these unit cells should not be interacting at all with what's going on in the next unit cell. So to that extent, by making the cells big enough, we're able to isolate the systems, and we really can study an aperiodic system of just these two balls of charge while using a method that really should work for periodic boundary conditions. So that part's good. So then we can go ahead, and you can imagine what you might have to go through to get the analytic result for the interaction of these two charge balls with themselves. I provided you the analytic answer on the assignment, and you can imagine doing this. You'd use Gauss's law, and you're integrating up the total charge within a Gaussian, so there's going to be some Earth functions, and you have to think about it and integrate by parts a couple times, and it's a little bit of a pain, but you can do it. It's no huge deal. But today, of course, we want to try a different approach to this problem, which is to try to go ahead and evaluate it analytically. Now, you'll notice I was at great pains to make sure that this charge distribution was neutral, right? I could have just put one Gaussian ball and calculated the electrostatic self-interaction of one Gaussian ball of charge, but I didn't do that. I clearly made the problem a little more complicated for myself by taking two, but I was very careful to make sure the system remained neutral. And maybe you guys can give me some thoughts on why do you think I was so careful? There's actually a series of reasons. Why was that so critically important? What would happen if I... Kendra, you go.
The energy of a charged system in periodic boundary conditions is infinite.
Right. So if you have an infinite system, right, the energy of an infinite system, of course, is infinite. I mentioned this earlier on when we dealt with some of the subtleties of how we solve Poisson's equation, right? The energy of an infinite system is infinite, but usually the energy of an infinite system per unit cell is finite because the energy is extensive. And the exception to that is actually if the unit cell contains a net charge. So if I had put a net charge in here, how do I put it? The self-electrostatic energy of that thing isn't even a well-defined quantity. Although my code would actually spit something out. You can try it. You'll get something. The question, what does that mean? Now, this is intimately related to a claim I had made when we talked about solving Poisson's equation. I had told you guys that, Poisson's equation has this problem, remember, when g equals 0, right? And I said that, the zero of potential is undefined in periodic boundary conditions. So we just arbitrarily set the constant component of the electrostatic potential to 0. And I claimed that would have no effect on the physical results because the zero of potential should have no effect. Well, here I can show you precisely that, indeed, that will obtain. Another way, as you know, our favorite way to write down the electrostatic potential energy is to write it as a single integral, 1/2 integral of this potential that we're solving for times n of r dq
If you
bar.
leave this with me,
And the point that I had made is, well, look, if you look at Poisson's equation and add to your solution any constant c, it's going to still solve Poisson's equation, right? So I could add any arbitrary constant, and I still solve the same equation. I can't determine that constant. Well, let's see what would happen to our energy if I added that constant, 2, the potential, and see if indeed there is any effect on the total energy. So if I did this integral, of course, then I can split it into my original answer, 5r times n of r dq bar, plus whatever constant shift I've added on, integral n of r times dq bar. Now you can see, right? As long as this system is neutral, then any constant shift in potential won't couple to the charge density, and I will get a unique, well-defined answer. That's why it's important to keep everything nice and neutral. When we go ahead and do the hydrogen atom or the hydrogen molecule, well, we'll put in 2 protons and 2 electrons. Everything will be neutral, and everything will be fine, and this constant shift then isn't particularly prominent. Okay, now, so that takes care of that, and so now we will get a unique answer out of our numerical calculation, and as I've said, we could also calculate this thing analytically. And I want to take a couple minutes then to comment then, before we go looking at the numerical performance of this thing, to kind of give you sort of my personal, philosophical take on computational numerical solutions to physics problems. Right? Because we've got, in this case, is a good example, we've got 2 ways to go. You can go the analytic solution or the numerical solution. Now the analytic solution, how do I put it? Even nowadays, I would say, though it's changing quite a bit, but you'll still get this sometimes in the older generation. There's a certain set of, to remain nameless, colleagues of mine who do not like numerical solutions. Right? They tend to think that, well, if you've solved it on the computer, probably you're not using your brain, right? That's a typical one we get, where you're just turning a crank. You're not necessarily understanding the physics of what's going on. Now, I would argue, though, and I'll give you an example from my personal experience, that the same thing is true of analytic work, right? That's just a basic failing of human nature. Everybody can be lazy at times and just turn a crank and crank out an answer, whether it's got the underlying physics right or not. Well, that's kind of up to you to be responsible to make sure you've done it. So an example we had recently, or last year, 2 years ago, I think it was, some research that came out of my group. How many of you here remember Johannes Lischner? He graduated last year. He's doing a nice postdoc off at UC Berkeley now. But one of his projects was looking at phonon-phonon couplings in carbon nanotubes. You guys have probably seen some of his work on that. And there, we had done like an analytic many-body theory type calculation to calculate phonon lifetimes. I'll spare you all the details, just give you sort of boil down to the essence of what the mathematical issue was. At some point, he had to calculate a scattering rate, and the many-body expression boils down to something that looks a lot like Fermi's golden rule. And so there was like this is a boiled-down version, isn't exactly what was happening, but it's got the same content. So there's some dispersion relation of phonon frequencies as a function of wave vector k. And maybe there's 2 branches here, omega 1k and omega 2k. And we're looking at transitions between these. It was actually a 4-phonon process, but this will give you the idea. And as you know how Fermi's golden rule works, you're going to integrate over all possible processes, and then there's usually some energy-conserving delta function, which in my little example here might boil down to something like this. Right? And then you know how this works. Well, integral of the delta function, well, you only get a solution where the argument's 0. So there's this nice point here, I guess, where you get a crossing of the 2 branches, and then you just get the inverse of the magnitude of the derivatives there, which would be the group velocity difference between the 2 different phonon bands. And actually, that was like a result we found in the literature. Now, it turns out, though, in real life, when you have like a carbon nanotube, it's clamped on both ends. It's a finite system. And so you do not have a continuous variable k to integrate over. Even though this is just how you're taught to turn the crank, right? You get like a series of discrete k points at a certain spacing. And it turns out, well, if you look closely, you're never going to actually have an exact coincidence of the energies of these two bands, right? They're likely just going to kind of just miss each other. Well, that's a little bit of a problem when you look at Fermi's golden rule like this, right? Now, the answer to that is that, well, in real life, and if you think about like where Fermi's golden rule comes from, there's always some time scale involved. So that this delta function isn't a strict delta function. It has a certain width associated with it, associated with this time scale. And as long as that time scale is such that these smeared out delta functions are wide compared to the spacing between the discrete points, then you can make the replacement with the integral, and everything works out just fine. And that's the usual assumption. That's why you do Fermi's golden rule this way. Turns out, though, in this case, no, the lifetime didn't quite work out that way. And you actually had to sum over all the possible discrete processes. So my point here is that, well, you know, that kind of, maybe you guys face it less than I do. I'm still touching on it. You know, years ago it was even worse in terms of the attitude about computational solutions. But you can still end up turning the crank if you're doing, you know, a many body theory calculation without thinking it through as well as you can in numerical. So the lesson is just pay attention to whatever you're doing. And along those lines, though, that's what I want to show you today, how we can accomplish that. Keep in mind, even the analytic solution that I gave to you ultimately is going to be a numerical solution. Because when you want to get an actual answer out to compare against some experiment, you're going to take maybe this closed form analytic expression, you're going to type it into your calculator and calculate it out to, you know, some number of digits. Right? And so my view is that a numerical solution is, in some sense, just as intellectually sound as a closed form analytic solution, provided, and this is the key thing, you have enough control over your numerics that you can calculate out your answer to whatever number of digits you would like. Right? It's like having a limiting process. How are the transcendental numbers defined anyway? Right? It's just, you know, a limiting process, basically. So if you have that kind of control, full control over the convergence to any number of digits you want, then I'd say you've got a full solution to the problem. It just happens you used a computer. That's my assumption. So we're going to try to approach that today with our solution of Poisson's equation. So maybe with that all said, let's take a look at how our solution is doing and see what we can do to approach that ideal. Now let's see if this will work. So hopefully you guys have run your thing. I'm going to run mine, so you guys can play along here with me. Let's see if this works here. So that's my Poisson code, and here is I'll run Octave. And you guys should run setup, and then Poisson. Oh, okay. Oh, that's much nicer. All right. So here's a picture. If you've run it the first time through, what it's doing now, it's just giving you pictures of the charge density in different slices through the center of the cell, either along the x-plane, the y-plane, or the z-plane. And you can see the first thing you should be able to get off of this is, well, when I'm slicing through the x-plane, because of my dimensions, I should be looking at a 25 by 30 grid of data. And sure enough, it's 25 by 30. So I'm looking at the right grid. And here's a picture of the total charge density, and like I had said, right, it's a sharp positive peak in the middle, then it's got a compensating negative peak that has a wider range, so it kind of goes negative as we go up towards the edges of the cell. And now, you know, you can step through this thing. If you hit enter, I believe you will get the next slice, which looks pretty much the same. It's just sliced in the plane along the second coordinate. The main point of these three is just to show you, well, now it should be a 20 by 30 grid, and sure enough, yeah, it was 20 by 30. We're just sampling things in at different spacings along the different axes, but you get the same kind of picture. And then this is the third plane. Nothing too, you know, super exciting there. Then it goes on, it shows you the, what does it show us next? It shows us the potential. And because this thing has a net, well, anyway, it just looks like the potential here, building up towards the center. Pretty normal. You might notice, there's a little, I think, negative excursion far away because of that negative Gaussian hits you. Its tail hits you first before you get in towards the center. And you get, 3 of those guys. And then finally the code finishes and you have a little printout here. And this is really what I want to focus on today. You have a printout here of the results and a couple of cross checks. And I want to see, what conclusions we can draw from these first. So, you see we're getting a normalization check on G1. Which one here is G1 here? He's my little negative guy. It's pretty close to 1. It was analytically normalized. The check on G2 seems to work much better. That's interesting. So they're both working quite well. And then finally, here's the comparison of the numerical and analytic Coulomb energy. And you can see, I guess we've got about 6 decimal places of agreement. About, 5 or 6 decimal places of agreement. So that's pretty good. But that's not what I want, right? I want to be able to controllably get this thing to match to whatever degree of precision I might desire to the analytic solution. Now, we're not there, clearly. But in terms of analyzing how a piece of software is performing, this helps us, though, narrow down what the likely sources of the errors are. Certainly, you're getting quite good agreement. So you can pretty much, right off the bat, and this is kind of a general principle, when you're getting this kind of agreement, you can pretty much assume you've done all of your derivations correctly and coded things up correctly. It's not 100% guaranteed, but you can pretty much assume that, right? I haven't missed some factor of 2 or pi in my answers, right? Which are easy to do analytically, but there's no way there's a factor of pi off there. And again, the odds that I've made some algebraic mistake in the formulas that I derive that would then lead to this kind of agreement, again, are pretty slim. It's not a mathematical proof, but that should convince us we've got the code functioning properly. So this must not be some analytic problem that we're facing, but a numerical problem. So what are the likely sources of the disagreement that we're seeing? What can we do to try to get this to match as good as an analytic solution? Yes?
We have a relatively sparse grid.
Right, we've got a sparse grid. That's number 1. Anything else on your heads right now? Sparse grid? It's a very important one. All right, well, we'll go with sparse grid then. So let's explore that. So what I'd like to do is actually have you guys rerun this thing with different levels of resolution, and we'll see how we do. But to do that, I'd like to go in first to the Poisson solver and comment out the statements which are producing all this graphics that are kind of getting in our way. So let me jump in here and do that with you guys. So, man, I need bifocals. Hold now. Okay, let's see. Where are these printouts? So you'll see about half a page down, there's this comment, visualize slices through center of cell. So we want to turn that off. And then there's another block below that. Again, it says visualize slices through center of cell. That's visualizing the Poisson equation. So it'd be good to comment that out. Save it, and then I'll run Poisson again, just to see how it behaves. And that's nice, because then it's just giving me my printout here without any of that graphics in the way. And I'll just leave this up for a little while, so you can see what the code blocks look like that I had commented out.